So in this video we will see about the Cortex M0 Plus, the processor. See, so far we have been actually learning about the Raspberry Pi Pico RP2040, which is a microcontroller, but now we are going to see about the processor that is present inside the microcontroller. We have already discussed that each microcontroller will have its own processor, right? Like Arduino has Atmega. This RP2040 has Cortex M0 Plus processor. Okay, so in this unit we will be seeing about that. In addition to that, we will also exclusively learn about NVIC, which is nested vector interrupt controller, like how we have seen in the previous video. Then we will also see about MPU, very important topic, memory protection unit, and then we have debugging, and then we also see GPIO. In addition to that, we also have DMA. This is a very important concept. By the second part of this unit will be DMA, direct memory access. We will see that in the next videos. So these are all the things that we are going to see one by one. There will be few repetitions, but I hope you will see through it. So Cortex M0. Cortex M0 is a processor which has very low gate count. That means that, or you can consider that it is being implied that having low gate count will have very high energy efficiency, and it is a microcontroller mainly made for embedded applications and in area where low power is expected, right? So we can consider this as a low power embedded application oriented processor, right? That is why Raspberry Pi, they have used Cortex M0 in their microcontroller, right? So by the end of this particular session you will be able to discuss the future of this Cortex M0 Plus. Okay, these are all the features. I know this is going to be very plain, but still, when I say tight integration, uh, the peripherals, as you have seen in the block diagram, almost everything is very tightly associated with each other, so that you can get things done very easy. Okay, uh, let's say there is a shop. Okay, there is a grocery shop. If you want to buy vegetable, you will go and buy that. If you want to buy a pen, you'll have to go find a stationery shop. If you want to buy something else, for example, if you want to buy fresh meat, you'll have to go find a butcher shop. But if you take a supermarket, everything will be available inside, right? There will be a area for meat, there will be an area for grocery item, there is an area for bakery items, right? Everything is placed very near to it, so you can easily access it and get things done, right? So that is what they mean here by tight integration. All the hardware is very tightly integrated. And then second point, thumb instruction. Thumb instruction means our microcontroller, our processor is 32-bit, so which can process 32-bit of information. But we can also program our processor in such a way that I can give the instruction in 16 bits. So that we will call it as thumb. Right? So when I say thumb instruction, I can give the instruction in 16 bits, so that instead of giving one instruction in a place, I can give two instructions in a place. So I can get things done very fast. Right? That is another advantage or wonderful feature in this Cortex M0 Plus. Then next one is single cycle input output, which we already discussed before. It will help us in getting our things done, the execution done in single cycle. So we have a dedicated hardware for that. Right? So we have seen in one of our previous video that Raspberry Pi Pico has dedicated hardware for multiplication, that is integer multiplication, integer division, and then we also have for interpolator, right, for interpolation. So that's what is here. Then power control optimization. We have power control optimization, where the controller can put itself into power control mode by gating certain architectural power connections. Okay, we call it as architectural gating. I can stop, or I can get certain hardware and I can restrict the power flow to that, so that I can have a optimized power control. Okay, we have so many hardwares inside this particular microcontroller. We have I2C, SPI, PWM, so many things are there. Let's say I'm using this particular processor based microcontroller for a very simple embedded application which does not require PWM. So in that case, I can do architectural gating, and I can restrict the flow to usually it doesn't happen, but I'm giving just an example. Right, you can restrict things and you can reduce the power consumption. Then the third one is, the last one in this area is integrated sleep modes. We have integrated sleep modes. We have different modes. One is one is sleep mode. Then we have deep sleep mode. So in sleep mode, the processor will put all the hardwares to sleep so that it will not do any work, so the power supply will also be conserved. Then there is something called as deep sleep, where almost everything will go to sleep except the set of registers which will wait for event signals. There is a signal called as wait for event, so it will wait for that. Once that signal is turned on, the processor will turn on. So you can put your microcontroller that is based on Cortex M0 into sleep mode as well as deep sleep mode. That way you can conserve the energy, right? And then we have fast code execution. This is also something very important. Maybe I'll share another interactive visualization that will help us in understanding. But now try to visualize any information that you give will be converted. Okay, remember I told Python is a script based language, so it requires interpreter, right? So interpretation has to happen. So any information you give has to be interpreted, and that interpretation has to be converted into the code. So any information that is getting is actually fetched, decoded, and executed. Fetch, decoded, executed. Fetch, decode, execute. So that is how the execution actually happens. So here we have a pipeline structure in such a way that when the first instruction is being executed or decoded, uh, the second instruction will also be fetched. So what happens is, at a particular time, 2 or 3 things can be done simultaneously. You will have a fast code execution, right? And then we also have optimized code fetching. So there will be an optimization where by which there will be a little time advancement through which you can get things done much more optimized. And then we have a hardware multiplier, which we have seen in SIO itself. In SIO we saw hardware divider, the same thing here but for multiplication. So imagine you are multiplying two numbers, 25 into 25. Okay, when you do this multiplication, what your processor does is, inside the software, where the processor, what it does is, it will add 25 plus 25, then 25 plus 25 plus 25, that is 125, again 125 plus 25, 150, 150 plus 20, like this it will do 25 such iterations to get the value 625. Whereas if I take a hardware, it will directly multiply and give me the answer. So what I have done is, I have my main processor. Along with that, I also have an extra hardware which will do certain multiplication, so that I don't have to burden my processor. So things can be done simultaneously, and this will give a better and fast execution of the processes, right? Then we have deterministic high performance interrupt. Deterministic, when something is done, deterministic in sense, we have allotted certain thing for certain interrupts. So it is deterministic. You don't have to go find where to do what is one. It's already predefined. Okay, that is the one advantage. We call our interrupts here as NVIC, nested vector interrupt control, and it is deterministic. And similarly, our instruction cycle is also deterministic. And then we have system level debugging and serial wire debugging. So you can debug directly on the processor. Okay, you can bypass the microcontroller peripherals, the bus fabrics, and you can directly touch the microprocessor and get things done, right? So welcome back to the next video. In this video we will be seeing about the configuration of Raspberry Pi Pico's microprocessor. We're going to talk about the microprocessor that is present inside the microcontroller called as RP2040. We know that the main processor that is present inside this particular microcontroller is Cortex M0 Plus. We have already discussed the features of this Cortex M0 Plus in our previous video. So in this video we will see about some important configurations in this particular microprocessor, right? So first one is architectural clock gating. So we could gate certain chips, certain architectural parts we can gate. When I say gate, I can restrict the power reaching to that particular hardware. So while doing that, what I can get is, when I do that, I actually get reduction in the power consumption. So that is one wonderful feature that is available in this particular microprocessor. That is why in the earliest presentation, when we spoke about this Cortex M0 Plus, we said that it is for low power and efficient systems, right? So this proves that architectural clock gating. And then second one is it follows a simple little-endian bus access. When I say little-endian bus access, what happens is that the information is actually taken similar to uh, FIFO, first in sorry, similar to LIFO, last in first out. You can see here, if you see this, so this is a 32-bit integer. So in this, the information actually gets stored in an order like, so the ones at the LSB will be at the top. OD is OD, OC next LSB, OB is MSB, OA is the actual MSB, right? So when the order is like this, we call it as little endian. Whereas if it is an opposite, for example, the MSB gets first, and then the next MSB, then the LSB, and then the least significant bit, the original LSB, right? So like this, if the arrangement is, then we call it as big endian, right? So we have a little endian system and a big endian system. So you should know what is little endian, what is big endian. So here we use little endian. That way we can easily retrieve the information starting from the LSB, right? When we write the digit, we always start from LSB, right? And then we proceed to the MSB. So in that fashion we have this little endian, we implement that, right? And then the next feature, next configuration that we can attain using this processor is that we get to have 4 breakpoints. Let's say you are typing some 100, 115 or 200 lines of program. If it shows if you throw some error, if you want to find where that error is coming, if you want to debug in the processor level, you can have this breakpoints. You can set 4 breakpoints for particular place up to which your program runs and tells whether there is any problem there or not, right? So, for example, if there is, like as I said, if there is around 150 lines of a program, if you are setting a breakpoint at 50th line, your code will first execute up to 50th line and it will tell whether there is any problem or not. If there is any problem, you can fix it. So by setting this breakpoints, you can actually do the debugging little easily, right? And then you also have direct debugging option, two wire, which is one is for serial wire debug data and the other one is for serial wire debug in clock. So one is serial data. So similar to our I2C, here SWD and SWCLK. So one is for debugging, the other one is for clock signal. And then we have this another important configuration, input output port, so which is a dedicated, which also features dedicated features like dedicated interfaces like you have I2C, SPI, ADC, tag. So all these hardwares are there already present inside your system, already present in your system, in sense they are present in microcontroller. But to communicate that particular hardware to your microprocessor, it needs some interface. So that interfaces are also already present in the microprocessor. So that is one important thing that to be noticed. So that is actually very important, and that also in a way is unique in this. And then we have 32-bit instruction fetch. So when I say 32-bit instruction fetch, it follows. And then we have this other configurations like we have 26 interrupts. Don't get carried away, we actually have 32 interrupts options available in this microprocessor, but in our microcontroller we are going to use only 26. And then we have 8 MPU regions. Okay, so MPU is actually your memory protection unit, which will allow the microcontroller to protect certain areas of the memory from unauthorized access. If you are storing some important aspects in a particular place, it should be free from disturbance. So we have set up, or we have segregated our memory in such a way that few will be accessed by everyone, but few will be restricted, so that you can retain, or you can store certain important information in sense some firmware kind of information, boot information in a certain place. So we call this as a memory protection unit. And then we also have some registers which resets on power up, so that will tell the status of boot up and other things. And then we have fast multiplier, which we have already seen. And then we have a SysTick timer, which is another feature. So this is for precise timekeeping. And then we also have an offset register vector table, which will tell the addresses. And then we have a 34 WIC interrupt controller. And then we also have DAP, which we have already discussed earlier in our previous video. So this is the functional description. As you can see, we have the processing unit, then a clock, then we have a reset control. This is our processor core. We have memory protection, then bus interface through which our high performance bus and single input output comes into the play. And then we have NVIC, which is the interrupt. Then we have wake up interrupt controller. So this is what is happening inside the processor. You can see here Cortex M plus processor, right? So this is present inside our microcontroller. And these features we have already seen. Most of the things we have already discussed, so you can just go through. And the NVIC features also we have already seen with some examples. So going forward, we know what is NVIC. Okay, SysTick timer we have already heard, but here it's a 24-bit system timer which will keep track of what is happening at what time. So if you want to know how much time has taken for a completion of certain thing, that can be done through this SysTick timer, because it keeps track of time, right? And then the power modes, which this is all something which we have already discussed in our previous mode. We have wake up interrupt controller, and then we have this important signals: wake up for interrupt, wake up for event, send event. So this will wake up the system if it is being under sleep or deep sleep mode. And these are all the certain registers that we use, right? And the memory, this we have already discussed long back. Another important thing that you should note here is we have 264 kilobytes of SRAM, static RAM. Of that, 4 are kept as a 16K banks, which will with each being 64 kilobytes, right? So you have 64 into 4, you will get somewhere around 256. To that you will have 4 KB. So put together you will get 264 kilobytes of RAM. So here we have segregated, as I stated before. These are segregated so that you can have a different access. Each will have its own path. So each can be addressed separately. That way you can do faster operation, right? So striped, that is what we call it as striped, which means separate address can be, or separate way of access can be done. That will enable higher performance due to faster access. Then there is non-striped SRAM banks as well. So they are for sequential access, one and then next. So this is for storing some certain important information, right? So with this, the features is over. In the next video we will see some other things related to the Cortex M0 processor. Thank you.